Okay, so continuing where we left off, we were talking about the fact that you will hear in your study of electricity people referring to conventional current, which is really from long ago, 1800s, when they thought it was positive charge flowing through the circuit. You will also hear people referring to electron current, which is what's really happening. It's the negative charge flowing from the negative end of the battery or power supply around the circuit. In the end, it doesn't change the math. If it's negative charge, if it's electron, then the current would be seen as coming out of the short side of the battery. If it was positive conventional current, it would come out of the longer side of the battery. Okay, and so in the last video I talked about the fact that this is the symbol for a battery, and really it's a whole bunch of cells. This is the symbol for a cell. It's a whole bunch of cells just stacked on each other. Think about the cells that are in your watch or in your calculator, and you can imagine that they're kind of like just a whole bunch stacked inside this. And depending on the type of battery you buy, sometimes you can almost feel the individual cells in there. Okay, so what's happening inside a battery? And we'll go back to current, but so the battery is doing work on the charge to move it across the battery, right? So let's suppose I have this in a circuit, and this symbol here that I'm drawing we'll talk about later, but it's a resistor. It could be a light bulb, it might be the microwave, whatever. Okay, so assuming electron current, then what happens is the positive side of the negative side of the battery, the positive, we'll start in the positive side, we'll start down here. So the electron is on this side of the battery, the positive end, and the battery does work to get it up to the negative end because the electron isn't going to want to go there, right? So you have to do work on it to get it there, and when it gets up here, the battery releases it, but it's at a high potential, right? A high potential energy, and nothing like staying in a high state of energy. And so as soon as it's released, it begins to move, right? It has potential energy. And the only route that it can move is through this nice convenient wire we have set up for it. So it'll flow through this wire, flow through this apparatus, giving some of the voltage that it's carrying to this apparatus to run it. And by the time it gets back to the battery, it doesn't have any energy left. And so the battery does more work on it and moves it across to the other side again. And so it picks up more voltage, right? So remember that voltage is equal to work divided by charge, right? Our equation up here. So the battery does work on the charge, giving it some voltage. The charge then flows through the circuit, losing that voltage to whatever it goes through, comes back with no voltage. The battery does work on it again. But think about the fact that the battery's doing work, right? How is it doing work? Well, there's actually a chemical reaction then happening inside the battery because the battery needs its own energy to do work, just like you do if you're going to do work. So there's a chemical reaction happening inside the battery, and it's the energy being released from that chemical reaction that then is being used to do work on the charge to move it across. That energy then is in that chemical reaction is why batteries die, right? If you've taken chemistry, you know that eventually all the reactants are used up. And so then the reaction can't continue anymore. And there are two different types of batteries. They're the kind that when all the reactants are used up, you have to take the battery out and throw it away and find a new one because it's done. But there are also batteries that are rechargeable. So what happens in a rechargeable battery is we stick this in a charger and we plug it in the wall. And so think of your chemical reactions. You know that some of them are reversible. Like they'll go one way spontaneously, but you can force them to go backwards by putting energy in. So that's what we're doing when we're recharging a battery. We're forcing all the products that are now in this used up dead battery, we're forcing all those products to go back across the equation and become reactants again by feeding energy in. And then once it's fully charged, once as much as the products as possible are back, then we can use it again. If you think of recharging a battery on a cell phone or one of the cordless phones at home, you know that the more you recharge it, the shorter the life it has. And again, if you think of chemistry, it's because when you force an equation backwards, the products back to the reactants, we can never get 100% of them back. And so the more and more we charge it, the more we lose gradually, until the time when your cordless phone will have just enough life to ring and you answer, and then it dies, and then you like throw it out the window because you can't handle it. It's so frustrating. Or the same with your cell phone, okay? But that's just to try to explain what you see happening with your batteries. All right, so work done. Now I want you to think of a battery almost like a chairlift on a ski hill, right? You're here at the bottom, and the chairlift does work to get you to the top. And then when you're at the top, you have all this gravitational potential energy, so you follow the path back down to the bottom again. The chairlift does work on you again, gets you to the top. So a battery in a circuit is exactly like a chairlift on a ski hill. And I think if you think of it that way, it'll help you make sense of what's going on inside the circuit. Okay, so here is one equation that we actually already learned. Now, a few minutes ago, we were talking about current, and I didn't finish it, so we should finish it. The letter for current, for some reason, is capital I. Okay, and current, we're now going from buildup of charge, right, that we had in the last unit, to that charge actually flowing. And that's really all current is. All current is charge that is flowing. Okay, from higher potential to lower. From high potential to lower. So it will only flow if there's a difference in potential. And that's what the battery is doing, right? It's moving the charge to a high potential and it flows to a lower. It moves it to a high, it flows to a lower. So if all points in the circuit have the same potential, no charge will flow. And that's what happens when the battery's dead, right? It can't do any work to give it that high potential, so nothing will flow. Another way of saying charge flowing from a high potential to a low is it's the rate at which charge flows. The rate. And you should know from all your math and physics by now, rate means there's time included. So the equation for current is just charge over the change in time. Okay, so this is our current equation. And our units for current, well, charge is coulombs and time is seconds. And so a current is coulomb per second, which we rename. We rename it an ampere after André-Marie Ampere, who would have been a contemporary of Volta. He did a lot of work with current, with electromagnetisms. Now, his full last name is Ampere, but we tend to say amps, and its letter is a capital A. Okay? Now, it's the amount of charge flowing in a particular period of time. So you could, like, don't do this, but you could, if you had really, good equipment, you could sit there with your stopwatch during isolation and count the number of electrons flowing in a wire in your house, in the wall, over a certain period of time, and you could find the current. Of course, you'd have to be able to see the electrons to do that. This Q is considered the total Q, and so you might come across an equation that would be like, we could figure out the number of electrons in that current, in that charge, like if we knew the total charge, by just dividing it by the size of one elementary charge, right? So if we found there were 8 coulombs flowing by, then we could figure out how many electrons would that be by dividing 8 coulombs by 1.602 times 10 to the negative 19 coulombs per elementary charge. The number I just rhymed up there is the charge on one electron or one proton. So this would just give us the number of elementary charges, just in case that comes up anywhere in your life. Okay, so today's practice questions are going to be with these two equations. Okay, very good.